Hi, it's John Williams here at MIT, and I want to talk to you today about the interplanetary file system. So this is a Stanford project, and some of the brilliant students at Stanford have come up with this idea of a distributed file system. So I'm going to cover today exactly how this system is set up and how it works. So the present internet looks something like this, that it has distributed nodes, but some of these nodes are connected to hundreds of thousands of other nodes. And so it's really not a totally distributed network, but it has central points of failure. And if, for example, the servers of Google go down, then we won't be able to find files and we're going to be in trouble. And so the present web is dominated by companies like Amazon, Google, Facebook, and Netflix. So, for example, one of the problems with the web is its present architecture, that it's architected with IP addresses, and we find material by the names of the files. So we have, for example, www.mit.edu/index.html, and this would be the web server at MIT, so it finds the machine, and the particular file is called index.html. Now, our system is optimized, but the question is, what is it optimized for? It has some very good properties, but there are some problems as well. For example, if Netflix has 1,000 people that want to view the latest movie that they've announced, then there are 1,000 different streams of bits. That movie is streamed 1,000 different times, and that may not make sense. So people have thought about how to redistribute things, that maybe we have a number of servers. And for example, somebody like Google certainly has thousands of servers. Even so, it's really taking the same idea. Now, what IPFS does is makes it really distributed. So this is kind of a little out of the box, if you like, but it might look something more like this. So the idea is that we're going to replicate these files across thousands or tens of thousands of servers. So the goal of the interplanetary file system is that it's a new hypermedia distribution protocol where the content is addressed by the content itself. IPFS enables the creation of a completely distributed application. It aims to make the web faster, safer, and more open. I should say not just one application, multiple applications. Now, what it means when we say that content is addressed by the content itself, if I have a file hello world, traditionally I'd have a name for that file, something like hello world.html or hello world.txt. Now what we're going to do is we're going to hash that actual content to get a number like this. So this now becomes the name of the file. And it looks a little weird, this hash. It's long. It's not like we could remember it ourselves, but it turns out that we can use these hashes quite effectively to find things in a distributed setting. So let me just remind you of what a hash algorithm is. For example, if we had a file with the word hello in it, that we might take the numeric values of the letters and add them up, and this would be a hash. Traditionally, hashes are much more complicated than this, but we end up with a hash that has a fixed number of bits. So typically it might have 160 or 256 or 128 bits, depending on which hash we take. So the hash is like a fingerprint for the document. If any of the characters in the document change, then the hash will change. And it's a one-way function in the sense that from the document we can get the hash, but we can't get it the other way around. Now, IPFS addresses issues with the present web, and those issues are that content at present is addressed by file name, and particularly that file will reside on a server or perhaps a cluster of servers. But if that server goes down, then that file becomes unretrievable. Also, moving large files is slow because traditionally they're streamed from a single machine. Now there have been, I'll mention BitTorrent, which does it a slightly different way and addresses that problem. So as I said, if many people want to watch a movie, the same bits are streamed many times. If a server is down, you can't get to the file. And also this centralized system here is vulnerable to cyber attack. There have been solutions to this. Git solves the problem by distributing the files over many machines. So for example, if you're part of a project, you'll clone a Git repository onto your own machine. Git happens to use these hashes for file names. If you look under the hood in Git, under .git/objects, you'll see these file names that are actually hashes. In Git, you have blobs that are the actual content. Then you have trees that are kind of directories that point to the files. And actually these trees in Git store the friendly file names as well as the hashes. We'll take a quick look at Git because this principle is used in IPFS. So what Git does, it stores these blobs under .git/objects. This was Linus Torvalds that developed Linux. He was very familiar with this Unix directories and file systems. And this is how it's dealt with there, that the hash corresponds to an inode or a file. So we developed the hash. Here I'm just showing them as 5 characters. They're 160 in Git. Basically, that hash will depend on the contents of that file. So if I revise this file and put, instead of just something, I put, say, something new in there, this hash would change. We have a tree that has its own hash, and that hash depends on these 2 hashes. Now, this is called a MERKLE tree. Now, what we notice is that one of the properties is that if either of these leaf nodes change, then the hash of the tree will change. And that is quite an exciting property. These are called MERKLE trees. So here I'm catting the tree file, and inside is this information that we have 2 blobs, and here's the hash of the blobs. One is hello world.txt and one is something.txt. Now these hashes have very nice properties. In Git, the structure forms a directed acyclic graph. So if you follow the arrows, you don't get cycles. So these are called DAGs, MERKLE DAGs. Several other software applications use this. They're called, in IPFS, they're called MERKLE forests. In Git, they're MERKLE trees. And Ethereum uses them and Bitcoin uses them. We'll take a quick look now at these MERKLE trees. So what we do is, the data block is the actual data. We create a hash at this level. So we have hash 0.0011011. Now we combine each pair of these. We take the first 2, and from that content, so those 2 hashes, we create another hash, 0. And the same with the second pair, 1. We again hash those together to get what we call the MERKLE root, or the top hash. Now, there's some very nice properties of these, and this is a slightly humorous diagram by Yunyan Chen, and I give you the internet address of that. But suppose we're trying to encode a banana. So we hash the banana. We're just showing 4 characters, A, B, 2, C. Now, let's suppose we encode 2 bananas. We might hash each of them, A, B, 2, C, and 7, 6, B, E. And now we can hash both of those together to get EF78. So we combine the hashes and get EF78. And if we now had 8 bananas, we can choose how we combine them. We could still get a single hash if we, for example, took all the hashes of each of the bananas, put them in a long string, and then hashed that string. So here we might get FF6D. An alternative, though, and this is the MERKLE tree solution, that we take up each pair and create this second tier of hashes. Then we create a third tier of hashes, And then finally, we hash those together to get the root. And so we could encode these 8 bananas in this kind of Merkle tree of hashes. Now, it has a nice property that if one of these bananas changes, let's suppose somebody takes a bite, so this is equivalent to a piece of data in a large data set being changed. If we have the structure on the left, we need the whole of the data set to recreate this top level root hash. But if we have this Merkle tree, we don't need the whole of the data set. We only need part of it. In fact, if this one changes, to create this 87CD here, we need 9B8F, that one and that one. Now, we're also going to need this hash here, the B09E, to combine with the 87CD to get 1E3C. And then we need this hash, 89D0, to combine it to get the root. But we don't need all of these hashes over here. So that's a very nice property. So we can easily verify that a data chunk is part of the bunch. And this is how Bitcoin uses it and how blockchain uses Merkle trees. They're very fast and require less computation than other structures. So you'll see Merkle trees used in a lot of different places. And as I mentioned, it's used in blockchain and Ethereum. Just showing here how a Merkle tree is used in blockchain. So for example, these would be transactions, transaction 0, transaction 1, etc. We create the hashes and then we get the root. So TX root is the Merkle root. Then we combine that with a nonce that solves the puzzle, and that the goal is to get leading zeros. And so we need to find what nonce combined with the Merkle root and the previous hash of the previous block and the timestamp, that we combine those together to get this final solution. So that's how the blocks in blockchain are formed. Okay, so as I mentioned, this is used in IPFS as well, and in Git, and in blockchain and Ethereum and other models. Now, we can layer a different model upon the internet. It doesn't have to be this centralized or decentralized. It could be totally distributed. And this is what IPFS does. So now in the second part, let's try and figure out how IPFS uses these hash names for its files to create this distributed network where it can find these files. So if I give it this long hash, it needs to be able to find what machines that hash is stored on. Now, BitTorrent addressed this problem of fast download from multiple servers. So this is Bram Cohen, and he developed BitTorrent. And let me show you how BitTorrent works. Files are sharded into pieces, and those pieces are stored on servers. And now when you request a file, so the way the shards are structured is into a Merkle tree. If we've got the root of the Merkle tree, we can get each of those shards. So we followed the Merkle tree down to the leaf nodes, and we know all the shards that we need to get. Now the trick is, how do we find those on this network of machines? How do we know what servers are storing what files? I'm running IPFS on my machine, and this is a diagram of the people around the world that are using it. And this was taken late at night, but parts of the world may run IPFS, but they were probably asleep then. But there's about 300 people running it when I checked. Now the solution to finding these hashes, these files that have hash names, is using distributed hash tables. And here's a list of some of the open source solutions for distributed hash tables. They have slightly different ways of handling these hashes, but now let me describe to you how distributed hash tables work. In IPFS, the files are addressed by their hash. And here's the file name, 980, this is the hash, and it returns hello world. The problem, if you like, that we're trying to solve is, how do we store these hashes? How do we decide what machine gets what hash? And then how do we find those hashes when I make a request by passing the hash to, for example, my server or a server on the network. So the solution is these distributed hash tables. And what we do, for example, we could take the IP address of the server and we could hash it and take the modulus with respect to, here we've got 6 machines. So mod 6, and that would give from the IP address, that would place the machine under either ID1, ID2, etc. And now what we do with the file is we take the hash and calculate which machine it's closest to. So the trick is, how do we get the distance of the file to the server? But that can be solved and has been solved. And so what we do is we place the files, so all the files in red here, or in orangey red, are closest to ID1. Then the blue ones are closest to ID6, the yellow to ID5, etc. And so now we need to be able to look those up. So we use an agreed on hash for the file name, and we use that as a key and assign ranges of keys to the servers. And I won't go into the details of how that's done, but all those distributed hash programs on GitHub are available. Now, the other trick is that we need to know which server stores what file. So a server needs to know about the other servers that are in this network. The network may be so large that it can't know about all the other servers. So there's a strategy of having, in IPFS, we have this BOOTSTRAP list. So these are some trusted servers. And usually what happens is that a server will store, for example, the nearest servers to it by some distance metric. And this is not a real distance. It's maybe a Hamming distance. And then it stores maybe the nearest ones after that, but they're not the nearest after that. So this goes in powers of 2. So we have 1, 2, 4, 8, etc. So it'll be a kind of a log, if you like, log to the power 2, that we'll have a table of servers. This is the BOOTSTRAP list in IPFS, which you can look up. And the MERKLE structure makes it very easy, for example, to shard files. So here we've got object 1, which is hello, and object 2 is world, and then object 3 would be hello world. So given this address, we can find the other 2 hashes and retrieve the shards. So, and this is the code for that, which is very compact. I'm going to give now an IPFS demo, and I've developed a video for that, which I'll show you now. I'm going to scroll this up so you can see the address. So if you want to watch this video, go to this address on YouTube and you'll be able to see it. So I'll just leave that there for a while, then I'll take any questions. So thanks very much indeed. Okay, I want to give you a quick demo of the interplanetary file system in operation. I've loaded it up and I made a video to show you how to do that. So now let's go to command windows, and the first thing we're going to do is bring up the IPFS daemon. So this sets up a server for us on our machine that can communicate to the other IPFS servers around the web. So you'll see here it's the swarm is listening on these ports, and this means that we can connect to other services, IPFS services out there. Okay, so now let's take a look. So I've got a directory here, and I've just got a couple of files in it. Here, Italy, and this. Let me add them to IPFS so that they can be seen. Okay, so now it returns a hash to me, and this hash is unique to this file. Okay, this hash is based on the contents of this file. and IPFS uses these hashes to identify files. So if a file is changed, the hash will change, and it'll be known by another hash name. And so that was Italy, and so I need to do IPFS add here. Okay, there you go. Now let's see if we can access those files. So I'm going to bring up a browser. So here's my browser, and what I'm going to do first is access the local system. I need to get this file name here, and there we are. Okay, so I can access my files under my own directory, so by my own IPFS directory via these, but I can also go and get that out on the network. There's a gateway.ipfs.io/IPFS, and that now went out to a remote machine out there and requested this. That remote machine figured out it probably didn't have this file itself, so it had to go and find out where this file is. It uses the naming system for IPFS to do that, to find out where this file is, get it from my machine and feed it back to me here through the browser. So that's a quick demo of IPFS in action. Let me just bring up and show you. There's a browser that you can download, and so here it is on localhost, and you can see who else out around the world is using IPFS. So here we are, and you can see there's a few people in Europe, there's a few people in the US. This is a weekend, so there's not too many people, and because of the time difference, probably there's not too many people running daemons across the world, but we've connected to 238 now. Okay, so have fun with IPFS.